let us now understand what is Kubernetes controllers in general. Okay. But before we move ahead to controllers in Kubernetes, let's see what does this controllers actually mean in a common sense term. So this controllers, right? Controllers are basically an infinitely running loop that keeps on executing as long as we have that application running. Okay. And the responsibility of these controllers is to monitor everything that is happening in the system. So to give you a real-time example, let's take something like a room temperature controller. Okay, so we basically have this thermostat installed in majority of the rooms, right? So whatever the current state of the room is, whatever is your desired state of the room, that is monitored by a thermostat. And thermostat continuously monitors if the room temperature is dropping or increasing. And if the room temperature is changed, right? So it brings it according to whatever the difference amount is there. So coming back to Kubernetes, right? Well, controllers in Kubernetes are basically like this control loop that watches the entire state of your cluster and then make or do request changes needed to be done. Each controller tries to move the current state that is closer to the desired state over here. So let us now move ahead and discuss some of the popular controllers that is available to us in Kubernetes. First off, we have something called as replica set. You see, replica set's purpose is to maintain a stable state of a replica pod running at any given time. As such, it is often used to guarantee the availability of a specified number of identical pods. You see, replica set ensure that a specific number of pod replicas are running at any given time. However, a deployment of a container is a high-level concept that manages the replica sets and provides directive updates to pods along with a lot of other useful features. Therefore, we recommend using deployment rather than just using replica set at once. So what I'm trying to say here is that you may never need to manipulate replica set object. Instead, you can just use a deployment instance over here. Alright, so speaking about deployments, right? So deployment basically provides a declarative updates for pods and replica sets. You describe a desired state in a deployment and the deployment controller changes the actual state to the desired state at a controlled rate. You can define deployment to a creative new replica set or to remove the existing deployment and adopt all the resources with a new deployment. So moving ahead to the next type, that is stateful set. This stateful set is a workload API object used to manage stateful application. This manages the deployment, scaling of the pod and provides guarantee that ordering the uniqueness of these pods. Like deployment, a stateful set manages the pod that are based on identical container specs. Unlike deployment, a stateful set maintains a sticky identity of each pod. These pods are created for the same spec, but are not interchangeable as they are referred to by unique identity. So moving ahead to the daemon set. You see, a daemon set ensures that all the nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, then those pods are removed and sent to a garbage collector. Deleting a daemon set will clear out all the pods that it has created. Some of the typical use cases of daemon sets are running a cluster stored daemon set on every node. Okay, running a logs collection on a daemon on every node. In a simple case, right, a daemon set covers all the nodes and would be used for each type of daemon. A more complex setup might use multiple daemon sets for a single type of a daemon. But the different flags or different memory and a CPU request for different hardware types are used here. So let us now move ahead and see what are Kubernetes services, right? So what do you understand when someone says what exactly is a service, right? Well, a Kubernetes service is a logic abstraction for a deployment group of pods in a cluster. Since pods are ephemeral, a services enables a group of pods which provides a specific function such as web services or image processing or whatever it is to assign a name and a unique IP address. As long as the service is running that particular IP address, it will not change. Services are defined like with different policies that goes there. Majority of the time we get asked what is the difference between service and a deployment. Well, you see, in Kubernetes, a deployment is a method of launching a pod with a containerized application and ensuring that this necessary number of replica is always running on the cluster. On the other hand, a service is responsible for exposing an interface to those pods which enable network access from either within or from outside the cluster. Alright, so now that we know a brief about what exactly is services, let us now move ahead and see what are the different types of clusters that are available. Starting off with cluster IP service. So the cluster IP service is a default type of service which is used to expose service on IP address internet to the cluster. This access is permitted only from within the cluster. Moving on to the next one, we have headless service. Services that do not need load balancing and only expose a single IP can create headless service by specifying none as the cluster IP. Headless service can be defined as a selectors, in which cases endpoint records are created at the API that modify the DNS to return address that point to the pods that are exposing the service. Headless services without selectors don't create an endpoint records. The DNS ecosystem configures either the CNAME record or the record of the endpoint with the same name as the service. Moving on to the next type, that is node port service. You see, node port are opening ports at every cluster nodes. Kubernetes will route traffic that come into the node port to the service, even if the service is not running on that particular node. You see, node port is intended as a foundation of high-level method of ingress such as load balancing and are useful in deployment. Moving on to the next type, we have external name service. External name services are similar to other Kubernetes services. However, instead of being accessed by a cluster IP address, it returns a CNAME record with a value that defines in the external name. Alright, so moving on to the last type, we have load balancer service. For those clusters that are running on a public cloud providers like AWS or Azure, creating a load balancer service provides an equivalent to a cluster IP service extending to a load balancing service that is specific to that particular cloud provider. You see, Kubernetes over here will automatically create a load balancer and provide a firewall rules if needed, and then populate the service with an external IP address assigned by the cloud provider. So now that we know Kubernetes services, let us now understand how can you access these services, right? So how do you access these services? Well, you see, services simply point to the pods using labels. Since services are not node specific, a service can point to a pod regardless of if they run in a clustered environment or not. Here, by exposing the service IP address as well as the DNS service name, the application can be reached to either methods. So how do you access these Kubernetes services is a question over here, right? Well, you see here there are two basic ways. First off, we have DNS, which is actually the most common way, and the other one is env variable. Talking about DNS, right? The DNS method is recommended method for discovering the services. To use this method, a DNS server must first be installed to the cluster. The DNS server monitors the Kubernetes API, and when new service is created, its name becomes available for easy routing and for requesting of an application. Next, as I mentioned earlier, we have env variable. This method relies on something called as kubelet adding environment variable for each active service for every node that is running at any given point. So to conclude over here, we can access Kubernetes services by two ways. One is by DNS and the other one is by env variable.
What is config map? In Kubernetes, according to the definition, a config map is an API object used for storing non-sensitive data. This data is stored in the key value pairs. These config maps are consumed by pods as environment variables or as configuration files in a volume. The benefit of this is that config map decouples environment-specific configuration from container images. This means that your applications can become more portable. Let's understand this a bit further. In Kubernetes, you can think of volume as a file system. Volumes are provisioned to the pods and owned by that pod. The contents of that volume can be mounted into any file system path we like in the pod's container. So, the config map contains the actual content that you are going to be using to populate a pod's volume or environment variable. They contain key value pairs describing file contents, environment variable, or some arguments. Now, let's look at the use of config map and its purpose. First, let's understand that when you create a pod, you use several environment variables. These values are tightly coupled with the pod. These values are normally typed in the pod's definition. For example, when you use a specific location, that is statically defined in the pod definition. Now, if you have multiple pods using the same variable, you will have to edit the pod definition one by one. So, you have to change variable, file location, definition, and so on. Kubernetes offers config map as a solution to this boring task, where you can define location as a key value pair, and that value will be injected into the pod. Now, If you ever want to change the values, all you need to do is edit the config map, and that's it. No more tedious work of changing variables and configuration one by one. This saves time and makes things simpler. So, let's talk about the similarities and differences of config map and secrets. First, in Kubernetes, these config map and secret might appear virtually similar, but the intended usage for both is a bit different. First, config map is strictly intended for storing non-sensitive information such as configuration data and environment variables. On the other hand, secrets is used for storing sensitive data such as passwords, tokens, and keys. Unlike config map, which has no encryption available, with secret, you can enable encryption in order to use it safely. Talking about the similarities, both objects are meant to be injected to the pods. But secrets is very specific and is intended to hold confidential data. Now, let's talk about how you can create config maps. Well, there are two ways you can create them. First is called the imperative approach and the other declarative. Let's look at imperative first. With the imperative approach, you can use the kubectl command followed by config map and the name of the config map and the key value pair with the literal parameter. The literal means that you are passing the key value directly during the creation process. These key values pair can be something like first name as a key and the first name like John as a value. With the declarative approach, you can use the file structure of config map and define key value pairs inside it. Then you save the file with an extension of YAML. Afterwards, all you need to do is run the kubectl apply command and provide it the file that you just saved. We will look into this shortly in the demo. So let's dive right into the demo and look at how to create config maps and use them in pods. Here I have my GCP master and worker node setup. First, I'll SSH into this session. Now, for this demo, you can go to the official documentation of Kubernetes. I have this page opened up. In my opinion, all you need to do is experiment with these commands. With a little bit of patience, you would be able to understand most of the documentation without any help. So, under this section that says create a config map, the first thing that we are going to be looking at these commands. So, as you can see, with this command, it first creates a directory of config map which is located inside configure pod containers. Next, it downloads two files from the Kubernetes website, which are game.properties and UI properties, and then pushes that into the directory that we just created. Afterwards, what it does is it creates the config map using this command with the config map name being game-config, and it passes it the file which are located in this directory. Therefore, in this manner, it is essentially creating config maps from directory because the directory will be holding two files. Let's do this. So first, I'll copy this command and essentially copy paste most of the code. Next, I'll download these two files and then we'll again be looking into this. Now, what I first want to do is I'll open these files. So as you can see, we have the UI properties with the key value pairs being listed like this. And the same goes for game.properties. So game.properties has these values, which is enemies equal to aliens, lives equal to 3, etc. etc. Now, we are not much interested in that, but what we are interested in is creating the config map using this directory. So if we look at my directory here, it has configure pod container, and if we go inside it, we should see the files that we downloaded. So it has the files downloaded here. Now we'll create the config map. This is done by using the kubectl command followed by create and then passing it the config map argument. Then we provided the name of our config map and follow it with the file argument. And then we provided our directory. In this case, it's configure pods, container, and config map. So we hit enter and we should have created our config map. So it says here we have created a config map and we can view this by typing kubectl get config maps. As you can see, we have created the game-config. Now, to view what's inside this, all you have to do is type in kubectl get config map followed by the name of your config map and then using -o YAML. So it has the game.properties values key value pair here and the UI properties key value pairs here. Now again, let's go back to the documentation. So we have created config maps from directory. Now let's look at how you can create config maps from just a file. So here, unlike last time when we passed the directory, we are just passing one single file and we are giving it the config map name as game-config-2. So let's create this config map. And in this case, our config map name is game-config-2. So because this time a directory was not passed, we should have only game.properties data in the config map that we just created. So let's verify this. As you can see, we have just the game.properties key value pairs here. And this was created using just one single file. Now, let's look at how you can use imperative approach to create a config map. What we did till this point was use a declarative approach in which files were already there and we just passed it to the kubectl create command. With this command, we use the from literal argument and we pass it a key value pair. Here, we are providing this key value pair of special how, which equals vary, and special type, which equals charm. So let's create this config map. This time, let's check how many config maps we have available. So now we have a new special config. Let's see what we have inside it. So as you can see, values that we provided, which were special.how equal to vary and special.time equal to charm, are available here. And now let's see how you can actually inject values into pods using keys and config map references. So let's go through the documentation and see what we have. So under this section, we can see that we are defining an environment variable here, which is from literal equal to special or how equal to vary, which we just did, as you can see here. Next, what we are doing is we are assigning the special.how variable to our config map, and we are doing this for this specific variable. So if you look at this, you can see that it has the name of the pod, which will be this. Next, it has a container, test container, and under the environment, it has a variable name called special level key, and it gets this value by referencing to the config map, which is named special config, and it references to the key of special.how, and then it creates this pod. So here, kubectl will be downloading the YML file and creating it right away. But what I'll be doing is I'll be copying this and then create it on my system. And now we have created our pod, which is named dappy test pod. Now, if we look at our documentation, it says here that we referenced special config and we have referenced the special.how key. Now, this should be reflected in the environment variable called special key inside the pod that we just created. which is named DAPI test pod. So to check this, what we are going to do is we'll type in one command which is called kubectl log followed by the pod name. And as you can see here, we have the special level key defined as very. And this is what we wanted to see. And with that, I hope you have a better understanding of what config maps is. This session was by no means a very comprehensive session on this topic, but at least with this knowledge, you can understand how config maps is used to inject values into the pods. So, do experiment and keep learning.
Now, before we understand what is operators, let's talk about site reliability engineering. So operators are basically software site reliability engineering. So what does it really mean? Site reliability engineering is a set of patterns and principles for running large systems. Originating at Google, SRE has had a pronounced influence on industry practice. Practitioners must interpret and apply SRE philosophy to particular circumstances, but a key tenet is automating systems administration by writing software to run your software. Teams freed from a rote maintenance work have more time to create new features, fix bugs, and generally improve their products. Now let's talk about operators. It is like an automated site reliability engineer for its application. It encodes in software the skills of an expert administrator. An operator can really manage a cluster of database servers, for example. It knows the details of configuring and managing its applications, and it can install a database cluster of a declared software version and number of members. An operator continues to monitor its application as it runs and can back up data, recover from failures, and upgrade the application over time automatically. Cluster users employ kubectl and other standard tools to work with operators and the applications they manage because operators extend Kubernetes. You must be wondering, what is kubectl? So kubectl is basically a command line tool for Kubernetes. You can really play around and operate Kubernetes with the help of kubectl command line. Now that we know what is operators, let us understand what are custom resources. So custom resources in short are used for small in-house configuration objects without any corresponding controller logic. That is, it is purely declaratively defined. But custom resources also play a central role for many serious development projects on top of a Kubernetes that want to offer a Kubernetes native API experiences. Custom resources are available in every Kubernetes cluster since version 1.7. They're stored in the same etcd instance as the main Kubernetes API resources and served by the same Kubernetes API server. At its core, a custom resource would look very similar to the image that you can see on the screen. Custom resources or CRs as extensions of the Kubernetes API contain one or more fields like a native resource, but are not part of a default Kubernetes deployment. CRs hold structured data, and the API server provides a mechanism for reading and setting the fields as you would those in a native resource by using kubectl or another API client. Users define a custom resource on a running cluster by providing a custom resource definition. A CRD is akin to a schema for a CR, defining the CR's fields and the types of values those fields contain. Now, Kubernetes provides custom resources to represent new collection of objects in the API. Custom resources are created and accessed by standard Kubernetes clients like kubectl, and they obey Kubernetes conventions like the resources.spec and .status. At their most useful, custom resources are watched by custom controller code that in turn creates, updates, or deletes other cluster objects or even arbitrary resources outside of the cluster. With this, let's move ahead and understand what are custom controllers. Custom resources are entries in the Kubernetes API database. They can be created, accessed, updated, and deleted with the common kubectl commands, but a custom resource alone is merely a collection of data. Now, to provide a declarative API for a specific application running on a cluster, you also need active code that captures the processes of managing that application. So the Kubernetes has a standard Kubernetes controller, which is called as the replica set controller, which we'll not be talking about as of now. But to make an operator providing an application programming interface for the active management of an application, you build an instance of the controller pattern to control your application. This custom control that you create checks and maintains the application's desired state represented in the custom resource. So every operator has one or more custom controllers implementing its application specific management logic. So now that we know what is custom controller and how it is related to custom resources, let's move ahead and talk about how operators work. So operators work by extending the Kubernetes control plane and API. In its simplest form, an operator adds an endpoint to the Kubernetes API called a custom resource, which we just talked about, along with a control plane component that monitors and maintains resources of the new type. This operator can then take action based on the resource's state, which is illustrated in the figure on the screen. Here on the screen, you can see that operators are custom controllers watching a custom resource. As I've already mentioned, custom resources are the API extension mechanism in Kubernetes. A custom resource definition, that is a CRD, defines a custom resource. It's analogous to a schema for the CR data. Unlike members of the official API, a given CRD doesn't exist on every Kubernetes cluster. CRDs extend the API of the particular cluster where they are defined. They, meaning CRs, provide endpoints for reading and writing structured data. A cluster user can interact with CRs with kubectl or another Kubernetes client, just like any other API resource. Now let's move ahead and talk about how operators are made. So the first thing what Kubernetes does is it compares a set of resources to reality. That is the running state of the cluster. Then it takes actions to make reality match the desired state described by those resources. Operators then extend that pattern to specific applications on specific clusters. So an operator is basically a custom Kubernetes controller watching a custom resource type and taking application specific actions to make reality match the spec in that resource. Now, making an operator means creating a custom resource definition and providing a program that runs in a loop watching CRs of that kind. What the operator does in response to changes in the custom resource is specific to the application the operator manages. The actions an operator performs can include almost anything, that is scaling a complex application, application version upgrades, or even managing kernel modes for nodes in a computational cluster with specialized hardware. Now, for example, the etcd operator knows how to perform particular tasks. An operator knows about its application's internal state and takes regular actions to align that state with the desired state expressed in the specific of one or more custom resources. Now that we know how operators are made to, let's talk about who are operators for. Now, the operator pattern arose in response to infrastructure engineers and developers wanting to extend Kubernetes to provide features specific to their sites and software. Operators make it easier for cluster administrators to enable and developers to use. Foundation software pieces like databases and storage systems with less management overhead. Now, if the killer new DB database server that's perfect for your application's backend has an operator to manage it, you can deploy killer new DB without needing to become an expert killer new DB DBA. Application developers build operators to really manage the applications they're delivering, simplifying the deployment and management experience on their customers' Kubernetes cluster. Infrastructure engineers create operators to control deployed services and systems. Now that we've discussed the major topics and terms in Kubernetes operators, let's move ahead and build our own operator. Okay guys, so now I am currently on Ubuntu. So what we're going to do now is we're going to build operators. For this, you'll need Minikube and kubectl already installed in your local machine. And you will also need cluster admin access to a cluster running Kubernetes version 1.11.0 or later. If you met these requirements, then you're good to go. So I'm just going to use the command sudo minikube version to check the version that I currently have on my Ubuntu, and it is version v1.20.0. Okay, and we are also going to check the kubectl version with the command sudo kubectl version space dash dash client. Okay, and this will give you the client version, it will give you the git version, git commit, go version, all of that information is here. Now that we have both Minikube and kubectl set up in our Linux machine, I am just going to start Minikube using the command minikube start. Now you can see that kubectl has configured to use Minikube cluster and default namespace by default. This is good. Now I'm just going to clear my screen. So before we move ahead, we are going to ask the Kubernetes API about the cluster admin role to see if it exists on the cluster. So you must be wondering, what is cluster admin role, right? Since operators extend Kubernetes itself, you will need privileged cluster-wide access to a Kubernetes cluster to deploy them. One such common cluster role is the cluster admin. Okay, so I'm just going to type this command to get a summary of the role with the kubectl's describe subcommand. Okay, now you can see that the RBAC cluster admin cluster role has been displayed. That is, the name is cluster admin, and also the labels, annotations, and policy rules have been mentioned. So now once you verify that you have privileged access to a Kubernetes cluster of a compatible version, you're ready to deploy an operator and see what operators can really do. A common starting point would definitely be the etcd, which is a distributed key value store with roots at core operating system, now under the auspices of the Cloud Native Computing Foundation. It is basically an underlying data store at the core of Kubernetes, and it is definitely a key piece of several distributed applications. Now, etcd provides reliable storage by implementing a protocol which is called as Raft. Raft, what it does is it guarantees consensus among a quorum of members. Now you can think of etcd operator as hello world, example of the value. Okay, so we use hello world as a beginner's program, right? So definitely etcd operator is a great way to start off with Kubernetes operators. So to use etcd, you put keys and values in and get them back out by name. So we'll learn how to really work with etcd. So for this, what I'm going to do is I'm going to firstly clear my screen. And so we will be downloading a Git repository for the chapters example codes. What this does is it grabs the chapters repository and changes into the particular chapter that we'll mention. So I'm just going to download this book by using the command git clone. So you can see that it is going to clone and download these chapters onto my system. And once that is done, I'm just going to change directory to chapters/chapter 3. So as with nearly everything in Kubernetes, a YML manifest describes a CRD. We've already talked about CRD in the theory part. A CR, that is a custom resource, is a named endpoint in the Kubernetes API. A CRD named etcd clusters.etcd.database.coreos.com represents the new type of endpoint. So what we're going to do first is we're going to be creating a CRD. A CRD defines the types and values within an instance of a custom resource. And this example defines a new kind of resource, the etcd cluster. So what we're going to do is we are going to type the command sudo cat etcd hyphen operator hyphen crd.yml. So you'll see a tiny piece of, YML file that specifies the etcd cluster CRD. The CRD defines how the Kubernetes API should reference this new resource. The shortened nicknames that help you do a little less typing in kubectl are defined here too. You can see that etcd class is given, etcd is given. Those are the short names that have been described. Now, what you can do is you can create the CRD on our cluster using the command sudo kubectl create -f etcd -operator -crd.yml. So you can quickly check if the new CRD has been created by using the command kubectl get CRD. You can see that the etcd clusters.etcd.database.coreos.com has been created. Now the CRs group, version, and kind together form the fully qualified name of a Kubernetes resource type. That canonical name must be unique across a cluster. The CRD you created represents a resource of version v1 beta 2 and kind etcd cluster. Now that we've created our CRD, let us clear the screen. So for now, what we're going to do is we just want to take a first look at the basic declarations for a service account and the capabilities that account needs to run the etcd operator. So we're just going to check out the file etcd-operator-sa.yml. Okay. And you can see the API version, you can see the kind and the metadata with its name. So you can create the service account by using the kubectl create command. Okay, and I'm just going to enter. Okay, my bad. And as you can see that the etcd operator SA has been created. Now, if you check the list of cluster service accounts, you'll see that the etcd operator SA also has been added. And you can check that by using the command kubectl get service accounts. And you can see that we have two clusters. The first one is the default one, which we saw when we started the minikube. So when we started the minikube by using the minikube start command, we saw that a default cluster had been created. You can also see that the cluster service accounts have been added. So the role governing the service account is defined in a file named etcd operator role.yml. So now what we're going to do is we give the role a name that we'll use to reference it from other places. I'm quickly going to type in the command sudo cat etcd operator -role.yml. And you can see that the YML file goes on to list the kinds of resources the role may use and what it can really do with them, that is, what verbs it can say. So you basically have verbs, you have API groups, you have resources, etc. Now, as with the service account, we're also going to be creating the role with kubectl. I'm just going to be using the command kubectl create -f etcd operator -role.yml. And you can see that the role also has been created. I'm just going to quickly clear the screen. Now, the last bit of the RBAC configuration is the role binding, which assigns the role to the service account for the etcd operator. And this has been declared in the role binding YML file. We're going to check that out. Again, we're going to use the cat command. So if you notice the last line, and if you're on a brand new OpenShift cluster, like that provided by code-ready containers, by default, your kubectl or OC commands will run in the namespace my project. Now, if you're on a similarly unconfigured Kubernetes cluster, your context default will usually be the namespace default that you can see on the screen. So wherever you are, the namespace value in the role binding must always match the namespace on the cluster where you're working. So now what we're going to do is we're going to create the binding. The role binding has also been created successfully. Now I'm quickly going to clear the screen and we will be deploying the etcd operator. Now the operator is a custom controller running in a pod and it watches the etcd cluster CR which we defined earlier. So the manifest file etcd operator deployment YML lays out the operator pod specification, including the container image for the operator you're deploying. We're quickly going to see how that looks. See, if you notice that it does not define the spec for the etcd cluster, you will describe the desired etcd cluster to the deployed etcd operator in a CR once the operator is up and running. Now, the deployment provides labels and a name for your operator. So some items that you will have to note are the container image to run in the deployment pods and the service account the deployment's resources should use to access the cluster's Kubernetes API. So the etcd operator deployment uses the service account created for it. As usual, you can create this resource on the cluster from the manifest kubectl create -f command. I'm going to just clear the screen. So I'm just going to create the deployment YML file. And once that is done, you can use the kubectl get deployments to check out the deployment. And you can see that the etcd operator deployment is ready. Now the etcd operator is itself a pod running in the deployment, and you can see that starting up by using the get pods command. I'm going to clear the screen. So now that we have created a CRD defining a new kind of resource, that is an etcd cluster. And finally, now that we have an operator watching the etcd cluster resources, you can declare an etcd cluster with your desired state. To do so, provide the two spec elements the operator recognizes, that is size, the number of etcd cluster members, and the version of etcd each of those members should run. You can see the spec stanza in the CR file. So I'm just going to check out the etcd cluster -cr.yml file. So this brief manifest declares a desired state of 3 cluster members, each running their own version of the etcd server. Now you can create this etcd cluster using the kubectl command that we used before. So this will be etcd cluster cr.yml. Okay, and you can see that it has been created. And we're just going to check out the pods using the flag -w. This example etcd cluster is a first class citizen, an etcd cluster in your clusters API. And you can see that it is initializing and the pod is also initializing, and now it's going to run. So you can see that the status of the cluster is up and running. With this, we come to the end of the session. So now let's move ahead and talk about the operators and how they've been adopted in various companies. A wide variety of developers and companies have adopted the operator pattern, and there were already many operators available that make it easier to use key services as components of your applications. Crunchy Data has developed an operator that manages PostgRE SQL database clusters. There are popular operators for MongoDB and Redis. Rook manages Ceph storage on Kubernetes clusters, while other operators provide on-cluster management of external storage services like Amazon S3. Moreover, Kubernetes-based distributions like Red Hat's OpenShift use operators to build features atop a Kubernetes core, keeping the OpenShift web console available and up to date. So firstly, we will understand why do we need stateful set in Kubernetes. So as I've already mentioned in the introduction, stateful set is used to manage stateful applications. What it really does in Kubernetes is that it manages the deployment and scaling of a set of pods. So the pods that you create in Kubernetes is simply a collection of one or more containers and is the smallest unit of a Kubernetes application. So stateful set really manages the deployment and scaling of a set of pods. Okay. The second reason as to why stateful set is required in Kubernetes is that it provides guarantees about the ordering and uniqueness of these pods. Also, unlike a deployment, a stateful set maintains a sticky identity for each of their pods. Replica pods of MySQL, for example, are not identical. These pods are created from the same spec but are not interchangeable. Each has a persistent identifier that it maintains across any rescheduling. The persistent identifiers are predictable pod name like mypod0, mypod1, instead of hash fixed endpoint or individual DNS name. So when a pod restarts, while the IP address changes, the name and endpoint stay the same. Stateful sets currently require a headless service to be responsible for the network identity of the pods. That is, we are responsible for creating this particular service. And stateful sets do not provide any guarantee on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in stateful set, it is possible to scale the stateful set down to 0 prior to deletion. The storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Now that we know why stateful set in Kubernetes is really important, let's move ahead and talk about what is Kubernetes stateful set. As I've already mentioned before, stateful set is the workload API object used to manage stateful applications. It basically manages the deployment and scaling of a set of pods and provides guarantees about the ordering and uniqueness of these pods. Like a deployment, a stateful set manages pods that are based on an identical container spec. Unlike a deployment, a stateful set maintains a sticky identity for each of their pods, and these pods are created from the same spec but are definitely not interchangeable. Each of them have a persistent identifier that it maintains across any rescheduling. We've already discussed these points in the previous part. Now, if you want to use storage volumes to provide persistence for your workload, you can use a stateful set as a part of the solution. Although individual pods in a stateful set are susceptible to failure, the persistent pod identifiers make it much easier to match existing volumes to the new pods that replace any that have failed. So in short, a stateful set is a Kubernetes controller that is used to manage and maintain one or more pods. However, so do other controllers like replica sets and the more robust deployments do. So what does Kubernetes use stateful sets for? A stateless application is one that does not care which network it is using, and it does not need permanent storage. Some of the examples of stateless applications may include web servers like Apache, Tomcat, etc. On the other hand, we have stateful applications. Now, if you deploy such applications on Kubernetes, you'll need to ensure that pods can reach each other through a unique identity that definitely doesn't change. Some examples of stateful applications include MySQL clusters, Redis, Kafka, MongoDB, and others. Now that we understand what a stateful set, let's move ahead and talk about the differences between stateful set and deployment. So at the heart of any Kubernetes deployment strategy lies the pod, the workhouse of distributed container solutions. The Kubernetes pod glues together a bunch of containers to a single networking stack and process namespace. Pod processes can communicate with one another over loopback and signal each other using signal mechanics. Deployments in stateful sets allow you to scale up your pods, roll out new images and configurations, and much more. But how do you pick which one to use for a given situation? It all depends on what you want out of your pods. So when your pods are interchangeable, you can use deployment. If scaling up means just run more of these, then you want a deployment. These are by far the most common in the wild, and they fit very nicely with application workloads and other 12-factor applications that share no state and have no need for identity. Let's say you have a deployment of a Rust-based web application. The load balancer out front routes traffic to the single application instance. The application itself keeps all state in the relational database behind it. So if you want to scale it, you have to just ask for more copies, as you can see in figure 2. Kubernetes deployment controller immediately springs into action, creating all of the new pods at once. Now, these new pods boot with the same environment variables set and the same config maps mounted in, presumably allowing them to talk to the database just like the first pod. The best use cases for deployments is when you want to use stateless application workloads and when you just want a single pod. Now we'll understand when to use stateful set. The 12-factor never be responsible for the data approach is a great one for commodity computation, like the kind of workloads that make up API services, backend service brokers, etc. Eventually, somebody has to actually handle data in order to make the whole thing worthwhile. Now, to scale stateful systems, you need a stateful set. Now, let's consider the relational database system behind the applications. Ideally, we'd like to be able to scale it up and build some sort of consensus-based leader or follower topology. We can't really discuss the details of how this would work, but suffice it to say that one cannot hold elections without identity. When we scale the stateful set from 1 replica to 3, the stateful set controller starts to incrementally deploy a new missing pods one at a time. First, the pod 1 comes up initialized and then settles into a ready state. Then the second pod does likewise. One of the more powerful features of a stateful set is the use of persistent volume claim templates, a means to provide each pod in a stateful set with its own persistent volume. Now, if you're trying to replicate database contents, this is a critical capability. The best use cases for stateful sets are when you're working with data services like databases, key value stores, etc. Or if you're working with identity sensitive systems like consensus systems, leader election clustering, etc. Or anything that really needs a slow rollout. Now that we know the difference between when to use deployments and when to use stateful set, let's go ahead and check out a stateful set example. So now currently I'm working on my Linux virtual machine. So if you want to try this on Ubuntu, you can follow this procedure. So before we begin, there are some prerequisites. Firstly, you will have to download kubectl, you have to download Minikube, you will have to download Docker, all of the procedure you can find in their official website. So install all of that and then we can get started. So the first thing that we're going to do is I'm just going to start my Minikube using the command sudo minikube start. Okay, so once that is done, you can see that kubectl is now configured to use the Minikube cluster and default namespace by default. I'm going to clear the screen. So sometimes running Minikube with the default resource configuration results in inefficient resource errors. So to avoid those errors, you can also start Minikube with start -- memory 2048 -- CPUs is equal to 2. Or you could just use the Minikube start command. I've already mentioned that stateful sets require a headless service to be responsible for the network identity of the pods. And we are responsible for creating this service. Stateful sets are intended to be used with stateful applications and distributed systems. However, in order to demonstrate the basic features of a stateful set, what we're going to do now is we will deploy a simple web application using a stateful set. So we're going to use a web.yml file which creates a headless service called the Nginx service to publish the IP addresses of pods in the stateful set. So what we're going to do is I'm just quickly going to open my web browser. So I'm just going to copy this web.yml file and I'm going to paste it on my web browser so we can view the entire file, the YML file. So I'm just going to explain this YML file really quickly. So firstly, there is a headless service which is named Nginx that is used to control the network domain. The headless service is created by explicitly specifying none for the cluster IP. So for the headless services, a cluster IP is not allocated. This is what we'll have to remember. So the stateful set, which is named web, has a spec that indicates that has two replicas of the Nginx container, which will be launched in unique pods. We must also set the .spec.selector field of a stateful set to match the label of its spec template metadata lab. And the volume claim templates will provide stable storage using persistent volumes. So I know we haven't learned what is persistent volume, but it is simply a piece of storage in the cluster that has been provisioned by an administrator. So that's what a persistent volume is. Kubernetes creates one persistent volume for each volume claim templates. In our case, each pod will receive a single persistent volume with the default storage class and one GIB of provisioned storage. Now, when a pod is rescheduled or scheduled onto a node, its volume mounts mount the persistent volumes associated with its persistent volume claims. However, the persistent volumes associated with the pod's persistent volume claims are not deleted when the pods or stateful set are deleted. This must be done manually. When the stateful set controller creates a pod, it adds a label statefulset.kubernetes.io/pod name that is set to the name of the pod. And this label allows you to attach a service to a specific pod in the stateful set. So I'm going to switch back to my terminal. First, what we're going to do is we are going to start with creating the stateful app. That is the stateful set along with the persistent volumes and the headless server. And we're going to do this using the kubectl apply command. So after the -f flag, I'm just going to paste the YML link. So you can see that we have created the headless server and stateful set successfully, which is defined in the web.yml file. And I'm going to open another terminal. And here we are going to use the kubectl get command to watch the creation of the stateful sets pods with selector flag. So I'm just going to use the kubectl get command. And you can see an output that is very similar to this. So you can see the status, you can see if it's ready, the age of it, how it restarts, etc. All of that you can see here. Now the pods I've already mentioned in a stateful set have a sticky unique identity. This identity is based on a unique ordinal index that is assigned to each pod by the stateful set controller. Now the pod's names take the form stateful set name ordinal index. Since the web stateful set have two replicas, it creates two pods, that is web O and web 1. You can see that on the screen, right? Now each of these pods have a stable host name based on its ordinal index. So as you can see that each pod has a stable host name based on its ordinal index. And we can also use the kubectl execution command to execute the host name command in each pod. Now when the pods restarted, the pods ordinals, host names, SRV records, and A record names have not changed, but the IP addresses associated with the pods may change. You can use the delete command to delete all the pods in a stateful set and wait for the stateful set to restart them and for both pods to transition to running and ready. And we can do this using the delete command. So I'm just going to first clear my screen and I'm just going to use the kubectl delete command. So it says the pods have been deleted. Now what I'm going to do is I am going to use the get pod command. Now the status is currently terminating. That means it is deleting. Now again, if I execute the command, it says the status is container creating. So there's a lot of things that you can really do in stateful set. You can write to stable storage using the persistent volume claims for all of the pods. You can also scale up via stateful set using the kubectl scale stateful set. So this is all to begin with stateful set. Let's move ahead and check out its limitations. So the storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Also, deleting and or scaling a stateful set down will not delete the volumes associated with the stateful set. This is done to ensure data safety, which is generally more valuable than an automatic purge of all related stateful set resources. Stateful sets currently require a headless service to be responsible for the network identity of the pods, and you are responsible for creating the service, which can be sometimes a limitation. Stateful sets also do not provide any guarantees on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in the stateful set, it is possible to scale the stateful set down to 0 prior to deletion. And when you're using rolling updates with the default pod management policy, it's possible to get into a broken state that requires a manual intervention to repair. So these are some of the disadvantages of stateful.